I'm going to give a pretty quick and informal overview of Zarr. Based on what we just heard, most people here are pretty familiar with Zarr. However, I think it's worth repeating some of the history and some of the fundamentals to explain, why Zarr is the way it is, and potentially also some of the challenges that we have in Zarr today. So let me introduce myself because I'm wearing a couple different hats right now in this context. The main one I'm wearing today is an open source developer. Helped start the Pangeo project, and for many years I've been working on packages like Xarray, Zarr, XGCM, Pangeo Forge, open source tools focused on making climate Earth system data more usable and accessible. I'm also a professor here at Columbia, and in particular, I thought I would say a word or two about what this space is and like where we are and why we're able to be here. So this space is part of a center at Columbia sponsored by the NSF called Learning the Earth with Artificial Intelligence and Physics. The lead PI for the center is a scientist named Pierre Gentine, and I'm also part of the leadership of that center. And the goal is really to take a step forward with Earth system models by incorporating AI into how those models are representing physics of the climate system. So it's a really exciting project. It's a 5-year project, $25 million award, the largest award NSF makes. And we're going up for renewal next year. And so this whole space and many of the resources that we're using for the sprint are supported by Columbia and the LEAP Center. And finally, my third hat is I'm actually on leave from that position right now. I've started this startup called Earthmover, where we're building a cloud-native database around the Zarr data model. So I'm very deeply invested in this community and this technology. Okay, so here's what I'm going to try to go over in my talk. I'm going to first explain what problem Zarr solves, why Zarr was created. And I'm going to give a high-level overview of how Zarr works. I'm going to run through some of the common use cases for Zarr today. I'm going to talk a little bit about the history of Zarr, which leads to the this question of what's next for Zarr, and sort of conclude with some sprint goals at a very high level. I'm not actually talking about GeoZarr specifically, and Brianna, I wondered if I could actually tap you after this to give a few slides on GeoZarr. I basically just didn't get it together. I was going to do it this morning, but instead we were playing with trying to get the AV and stuff working, but that would be awesome. Okay, thank you. Cool. Okay, so level setting here. There is a data structure in computational science called a multidimensional array. Sometimes perversely called a tensor. I'm very opposed to this this nomenclature, but that ship has sailed. And this is a foundational structure for computational science, right? So all numerical programming languages that are focused on scientific computing, whether it's MATLAB or Fortran or Python or Julia or Rust or what have you, this is sort of the core data structure for how we represent structured scientific data. And so these arrays can have shape ranging from 0, just a single scalar value, one-dimensional arrays. Two-dimensional arrays are very familiar to us. We tend to call them images. Three-dimensional arrays are cubes. And we have data sets in Earth system science that go up to 4, 5, 6 dimensions, right? And so this is these have a wide range of applications. There are obviously many in geospatial and Earth system science, also very heavily used in bioinformatics. I mentioned the T word, tensor. These data structures are central to modern machine learning and AI, right? TensorFlow, both for the input data to such models and actually how the neural network weights themselves are represented. And of course, throughout simulation and computational science, so here's just a random picture that Tom helped me find from a plasma physics simulation about, anytime you're essentially trying to represent the physical world inside a computer, you're using this type of data structure. Okay, so how then when we want to store, save, and share these types of data sets, what choices do we have? This is sort of the layout, the landscape, before Zarr came onto the scene. And this isn't necessarily meant to be comprehensive. This is just representative of what types of storage technologies are out there, right? So we have, of course, our sort of generic scientific file formats. NetCDF, very common in Earth system science. HDF5, really the model for the actual data model for Zarr came from HDF. So who here is familiar with HDF as a file format? So yeah, many people, right? What we see a lot, of course, are very domain-specific file formats, designed custom-made for one field's specific needs, right? So GRIB is an example I picked for meteorological data and forecast data. And I'm sure in your subfields, you all are familiar with some weird, bespoke file format that got invented by somebody. And it seems like a good idea at the time, but I feel that this is a real anti-pattern for interoperability, actually, to keep inventing new custom file formats. And then, of course, we've got, as an array format, we have a heavy intersection with image formats, right? So as I said, an image, you can think of it as a two-dimensional array. So, there's an intersection between imaging technology and Zarr, particularly around the bioimaging community. Now, I would contend that the main reason Zarr came into existence was around the challenges associated with big data. If you got small data, any one of those formats probably works fine for you. Just email it to somebody, right? Like if you want to share it. And I'm going to use that term to describe those formats as monolithic file formats, where all the data is in one file. I'm also going to use some of these awesome cartoons that were actually commissioned by NumFocus for Zarr to illustrate some of these challenges, right? So the challenge we have today is it's possible and also quite desirable in many cases to construct really huge arrays. So for example, modern light sheet microscopy can scan tissue and generate a single contiguous 3D cube of data that is over a petabyte in size, right? It's one logical object. Similarly with Earth system models, we can run a big high-resolution climate model, dump out the state of that model, different state variables on its three-dimensional grid over at high time frequency, and all of that conceptually can be thought of as one single large array. Did someone have a question or comment? Please jump in if anyone wants to say anything here. However, it's not really feasible or practical to put more than a few gigabytes of data into a single file. Yeah, you can do it, but there's a lot of reasons why you wouldn't want to. The main one that sort of motivated Alistair Miles, the creator of Zarr, is that it's really hard to write those files in parallel. So we don't have a lot of technology that's able to create a very, very large single file and write to it in a distributed fashion with low coordination between those processes. In particular, in cloud object storage, it's impossible to do that. There's no way to have multiple writers easily writing to the same object or file. Even if you had, say, a terabyte size file with your big array in it, that would not be a very convenient object to move around and work with. It would create a lot of friction for you. A sort of related motivation is that many of these legacy monolithic formats don't work particularly well in the cloud. However, that is actually not the primary reason that Zarr was created. It's sort of a use case that emerged later. So what problem is Zarr solving for us? It's really providing a way to store really big arrays and read and write to them in parallel. Okay, so I'm trying to be practical here and give a definition of what I mean by really big. 10 gigabytes or larger. If you've got less than that, you probably get away with one of the monolithic file formats just fine. Also, you don't, of course, have to read them in parallel, but when we're talking about that scale of data, all operations tend to work better if you can use parallelization or concurrency while accessing your data. So that's sort of the high level, right? And I think it's important to state this very clearly, because often in the, in geospatial, there's a question about like, well, what format is better for what use case, and why should I use, Zarr or GeoTIFF or this or that? And I think this is a really good criterion for thinking about, like, this is why Zarr exists, for big data. So how does Zarr do that? Well, it's really simple. It takes the data and spreads it over many files, but you as a user don't interact directly with those files. The Zarr technology is able to address that collection of metadata and data objects as one consistent logical object, right? And so it breaks down this relationship between your logical data set and the physical file, right? So here's a fun like cartoon illustration of that. The way a microscope would probably scan this tissue is, by slicing through it at different levels. And in a monolithic file format, you dump that all into one big 120 gigabyte file, whereas with Zarr, you're able to chunk it up and provide much more efficient access. Also, serve it over the web and do all kinds of cool stuff. So that's the basic idea. So what is the Zarr data model? It's really deliberately modeled after the HDF data model. It contains most of the same structures and objects. So it's deliberately generic, right? It doesn't provide any domain-specific conventions. The focus is really on that storage layer, providing efficient I/O to that data. And so Zarr provides you with groups, which are like folders that you can then put arrays into, specify the data type, shape, and then attach metadata, arbitrary, key value metadata to any of those nodes in that hierarchy. So it's designed to allow domain-specific communities to, put their own conventions on top of this data model, just as they do today with Zarr. So in bioimaging, for example, they have the open microscopy environment next generation file format, which is essentially a specification on top of Zarr. It doesn't change Zarr. It just says, this is how we're going to use Zarr to store our type of data. Similarly, in weather and climate, we are effectively using NetCDF and CF conventions together with Zarr to store weather and climate data. And in geospatial, we're trying to figure out the right way to do this through the GeoZarr effort, and have not fully aligned on one best and right way of doing it. And that's part of what we're hoping to move forward with the GeoZarr OGC working group and at the sprint today. Now, as far as storage, this is another really important concept for Zarr. Zarr is not a file format. Like I think I've already tried to make this really clear. Like Zarr is a sort of hierarchy of different data objects, metadata, and chunk data that are stored according to a schema. And Zarr was deliberately designed to allow you to put that into any type of storage device that can be represented as a key value store. Plenty of people use Zarr in memory as a way of having lower memory footprint. So using compression, keeping the data in memory compressed within a Zarr data structure. Obviously, a file system is a really common way to use Zarr. Just put the Zarr data in files on your computer. Or similarly, you can put that same data in the same schema in cloud object storage. But you can also do more exotic things like put Zarr into a database. Folks have put Zarr into Redis, MongoDB, SQLite. It's deliberately designed to allow you to have that sort of flexibility. And so just putting quickly on my Earthmover hat, this is kind of what we're doing in our company, is we're designing a sort of customized storage layer that's designed to really understand this data model so that you can use the generic Zarr data model, but have like a much more full-featured storage backend to put it into. So just for a little context there. Okay, so how does the Zarr community work? So crucially, Zarr is an open source multi-stakeholder project, right? There is not one single company, organization that owns and controls Zarr. This is really important to the success of Zarr. And I'll give a really specific example about why a lot of the public sector US institutions are very excited about Zarr. NetCDF, which is our core storage technology for geospatial, or let me just say Earth system data, is maintained by the Unidata folks, part of UCAR. And it had been based on HDF and still, of course, uses HDF very heavily, which is an open source single stakeholder project. HDF is controlled by HDF group. They make all the decisions about what happens. And HDF group decided to introduce some changes to how they were doing HDF that included some proprietary features that were not going to be released open source as part of that core storage library. And that really freaked out the folks at Unidata, probably a lot of other data providers, this sense that they were dependent on that type of governance. And so Zarr is deliberately not controlled by any one entity. It's a community governed project like many of the folks and many projects in the Apache world or the NumFocus world. The trade-off of that is that that process can sometimes be a little slower to move and evolve than something that has a single stakeholder and an executive who can just decide exactly what's going to happen. And I think that's really important context for everyone to think about, right? What are the pros and cons made in that sort of trade-off, right? So Zarr sort of consists of the implementations, right? And so here you can see there's more than a dozen different implementations of Zarr in different languages for different purposes. The reference implementation has always been Python, the Zarr Python library. That's where Zarr was created. However, ironically, Zarr Python has now fallen behind some of these other implementations in terms of its maturity. And that's something we're trying to really fix very rapidly, and we're going to work towards that today. And then, so each of those implementations kind of does what they want. Like no one tells Jeremy over at TensorStore, what he should do. They govern that project the way they want. Yeah, go ahead. No, please interrupt. Yeah.
Just curious about that last point. What, libraries here do you consider the most mature?
Well, regarding the implementation of the V3 specification, which is like the latest iteration of Zarr, TensorStore for sure, Zarrita. It was how it was prototyped, which is just basically a more newer, more modern, but very experimental Python implementation of the new Zarr standard. And then actually this new Rust library is pretty cool. Zarrs, there's 3 different Zarr Rust crates. However, like I see it as part of my responsibility and of like other Zarr Python developers to very rapidly get that Zarr Python back as a sort of gold standard reference implementation, because that's where Zarr has the most users today. And so that's where we'll get the most impact.
And can I just do one quick follow-up?
Sure, totally.
So I've played around with Zarr Python, actually not where Zarrita, and I've also worked with the Rust Zarr library a fair bit. And within the kind of model you're seeing in a lot of these different libraries, like Polars and whatnot, or Pydantic, do you think there's a potential for like kind of like a back end sort of swapping thing where we can use Rust under the hood and then Python interface?
Yeah, this is a great question. It's definitely possible. One interesting thing about Zarr, in contrast to like most other file storage formats, like say HDF, the way HDF works is there's basically one implementation in C, and then every other programming language binds to that. And they have to figure out how to like get that dependency built. And if you've ever tried to compile tool with HDF library, there's a trade-off there in complexity. Now, Zarr being so dead simple, traditionally, when a new language wanted Zarr, they just implemented it from scratch using the native, conventions of that language. We could move to what you're saying. If there's a sort of core, Rust or C++ implementation of that library, and then all these other languages would bind to that. We're definitely exploring those ideas in Zarr Python. But it's not how things have traditionally been done in the Zarr community. And it does create a barrier to like the hackability of the library, which is one of the key, good things about Zarr. It's simple enough that normal programmers can kind of just get inside it and start tweaking things and try new ideas. And if it's just written in pure Python, that's straightforward to do. But if now there's a compiled layer in another language, that barrier gets a little higher. So I think we should have both. I think we should have a native Python implementation, but I think there's also room for certain elements of that to be implemented in a more high performance language. All right, we got to keep moving forward here. So let me carry on. So in terms of the project-wide governance, this applies really mainly to the spec. which is the thing that all of these implementations share and have in common, right? They're all different implementations of the way to read the same format. And so the governance for the Zarr project as a whole is focused on that format. There's a 5-person steering council. It's a committee of equals, but I really want to shout out Josh Moore as someone who has been doing a lot of the heavy lifting of making this governance work and be possible. I'm on that steering council and, you know, do way less work than Josh. We have a mechanism modeled after NumPy enhancement proposals or Python enhancement proposals for how the community can propose changes to the spec and involve the Zarr format. And that's how the V3 spec has been developed. That's how some of these extensions that I'll mention are being developed. And I want to just say clearly, like, we're still figuring out how to do this. And as I'll figure out as I'll explain in the next few slides, like, you know, it's not very simple to do this type of community-driven spec development. We've learned a lot over the past years. And I just want to like make it clear to people, like, this is kind of work in progress, figuring out how to do this as a community, as opposed to just like one company just sitting down and being like, this is the way it's going to work. And we have to really acknowledge the Chan Zuckerberg Institute, the Essential Open Source Software Program, as providing critical support to the Zarr project. It's funded the ability to appoint a community manager. This is someone named Sanket Verma, who's been very helpful, perhaps on Zoom, in sort of stewarding the Zarr project. Okay, so moving quickly to one of the more sort of technical aspects of Zarr that we all probably are familiar with. So Zarr gives you this total flexibility around how you want to chunk up your arrays, right? And this is both a great feature and also big potential foot gun for users of the library. And I imagine many of you who use this are very familiar with the trade-offs that come when choosing these chunks, right? So very often our data generation process creates something that we like to describe as pancake-based chunks, right? Layering essentially one image stacked on top of another. It's a very natural way to create data. Sometimes the way we want to analyze that data means we want to drill down along a single point, say extracting a time series, which is a completely orthogonal organization of the data from this one. And then an intermediate choice is sort of isotropic chunking structure. Scones, Yoni helped come up with a lot of these terms, by the way, is kind of not great at anything, but also not bad at anything, a good compromise. So, you know, a lot of the, I think, work around Zarr is thinking about how to make this a little easier, how to make this more user-friendly. But, you know, this problem has always existed. It's not, Zarr didn't invent it. It just sort of, it surfaced it for us all to see and confront. That's the way I think about this. Okay, so I was going to put a lot more images on this slide, but I kind of ran out of time. How is Zarr being used today? Well, it's got a pretty heavy footprint and very mature adoption in bioinformatics, particularly on bioimaging and genomics. There's actually a big contingent of folks recently learned using Zarr in the context of financial data. A lot of hedge funds and folks like this are storing market data in Zarr. They like that multidimensional data model. that was interesting for me to learn. Then over on the right, I've got sort of everything Earth related, right? Earth system models were really like the first big, use case for Zarr in our community. And in our lab, we brought 2 petabytes of CMIP6 data into Google Cloud and AWS public dataset program in Zarr format, and that's still there today. Julius works on maintaining that data set. And I think that's had a huge impact. Weather is a big fit for this. Folks have mentioned hydrology, and we're starting to move also into the Earth observation space, particularly around data cubes. You know, when folks say data cube, the minute you hear that cube, that's kind of sort of trigger, oh, this could be a good fit for the Zarr data model when you have these sort of regular organized Earth observation data that's been harmonized spatially and temporally. Okay, so here's, I'm sort of wrapping up. Here's some of the history. There's many important things that I'm leaving out of this, but some of the relevant points. So Zarr was created in 2015 by Alistair Miles, a genomics researcher at Oxford University, for storing genomic data. And he created it because he was sick of trying to write HDF files in parallel, and he wanted something simpler and easier to parallelize. So, this is perhaps a me-centric perspective on Zarr, but like I'm really excited and proud of what we did in 2018 when we plugged Zarr into Xarray, because that gave us an ability to create all kinds of Zarr geospatial data. You could read netcdf in one line and write it in Zarr in a second line. And all of a sudden we had this new format that was completely interoperable with our existing data. And that drove a lot of adoption in our community. Zarr became a NumFocus sponsored project in 2019. And in 2020, Alistair stepped back. This was Zarr was essentially operating under a BDFL, benevolent dictator for life governance model. And then that dictator decided to, retire. He's still around, but he's not leading the project anymore. And so Zarr started to transition to a community governance model, and sort of want to be open about some of the challenges that created in the Zarr community. This kind of hit right around the time the pandemic started. It was a crazy time for everyone. And in many ways, we kind of lost some momentum on the Zarr project around that time. Between the governance transition and everything that was happening in the world, Zarr slowed down a little bit. And I think that's created some frustrations in the community. And that's precisely what we're trying to, overcome today. But Zarr kept moving forward, of course. It was adopted as a OGC community standard, Open Geospatial Community Standard, in 2022. Last year, we finally got this V3 spec approved and getting implemented. And in 2024, I see a ton of momentum in this community and a ton of potential for Zarr. So that's a bit of history about, how we got there. I'm sure I left out many important points. So what's next? Where are we headed? Well, this Zarr V3 is very exciting. And I'm going to say a little bit in the next few slides about why V3 was created. What's the point? There's also this, formalization of the Zarr conventions. So we mentioned that a lot of communities are using Zarr in different ways, and we're working on sort of formalizing a bit more so other communities can discover those conventions and reuse them, and et cetera. I'm also really excited about this concept of virtual Zarr data. So I'm not going to say too much about this, but who here has heard of Kerchunk? Yeah, so just about everyone. So it's this idea that actually we can use Zarr as an interface to retroactively cloud optimize all of these monolithic file formats, that we can take netcdf data or HDF data and actually build an index and then query it using Zarr's data model without actually writing new Zarr data sets. And to me, that's really exciting. And it suggests an evolution of Zarr beyond just like a file format to more of a protocol. And I think that's a really exciting evolution and something that we should continue to explore and invest in. So coming to the end, Zarr v3. Why did we have to create this? I said shortcomings in the v3 spec. I meant to write v2. Zarr v4 will be addressing the shortcomings in the v3 spec. But for right now, this is what we've got. So a big motivation for creation of this new major version of Zarr is interoperability. Despite the fact that there were other languages implementing Zarr, there's a lot of Python stuff baked in to the v2 spec around data types. And so it was really important to us to make the specification completely agnostic to the language. That's one. Two is extensibility. So I've already mentioned Zarr is simple, it's hackable, but the v2 spec contained no extension points and no mechanism to add features or change the spec really in any way, which is this sort of like foundational problem for evolving it, right? So you have to break it in order to enable extensibility. And hopefully we'll never have to break it again, because now we have extensibility and now we can add optional features or new things to Zarr without having to do some major big breaking change. High latency storage is another motivation. By high latency storage, we're really talking about cloud object storage. Zarr is used heavily in the cloud today, but actually didn't necessarily designed for cloud. It was designed for big data stored in file systems. And so making Zarr even more cloud friendly is a big part of the motivation for moving to v3. And finally, we want to enable more flexibility in the storage layout. And you might think of this as like an extension, but one of the most important extensions that we've wanted to develop in Zarr that wasn't really allowed by v3 is what I'm going to talk about next, which is called sharding. So many of you may be familiar with this. So in Zarr, the v2, what I originally presented, was basically a one-to-one correspondence between your file and your chunk. Each file is just one giant blob of compressed binary data. And for many of the use cases, analytical use cases that were developed, Zarr was developed for, those chunks would be 10 or 100 megabytes of data. And the only way to read that data is to get the whole chunk and download it and decompress it. A lot of applications don't like that pattern. They want to be able to peek into that chunk without downloading the whole thing. Very much the same problem in a way that GeoTIFF versus cloud optimized GeoTIFF dealt with, but this time at the actual individual chunk level. So Zarr v3 sharding breaks down this one-to-one correspondence and defines a new thing, which is a shard, the unit of storage, the individual file. And then within that, we can have many chunks, which is the unit of compression. And so this is going to enable more use cases for Zarr, particularly like this is important for visualization if you want to just pull out a little bit of the data quickly, and also like fast selection of individual points. This is implemented at various levels. This is fully implemented in TensorStore. It's fully implemented in the Zarr Rust library, and we're working on getting it into Zarr Python.